Alright, I just got this question. I know how to find the test statistic Z. I know how to find the p-value. What do these two do? What do they prove? I'd like to know more than just knowing how to use the equation. Alright, so let's say that you just conducted a hypothesis test. So no matter what, when you do the hypothesis test, if you standardize it and you make it a Z or a T or any of the other distributions, typically, especially for Z or T, when we standardize, we get a bell curve with 0 at the center. And no matter again which one we compute, the test statistic will be some number. Let's say down here somewhere. So let's do T. So let's say that this is our test statistic. So you know that this is the test statistic. You know the area of this shaded region right here is your p-value. But what does that mean? What does it mean if the p-value is some tiny little number? Well, what the test statistic is the z-score, or t-score, the number of standard deviations away from what the expected value or the claimed value of the mean or the proportion or whatever, the value from the population you're trying to measure. So how far away are we from our claim? The idea is we are typically close to the claim value when we sample. If we're trying to predict the mean of a population, the sample means that we would get if we took a sample of a certain size, the sample mean should be close to that claim mean. It should be in here near the center of the distribution. We shouldn't be at the tails of the distribution if the claim is true. So if the claim is true, how far we are away from the claim value of the mean or the proportion should not be very large. We should be relatively close to it. But the further and further and further we are away from the claim value of the mean, the bigger and bigger and bigger that test statistic will be. It'll start being a much larger value. And because that measurement, how far we are away, is basically in these distributions in Z and in T, it's how many standard deviations we are away from the claimed value. So the further we are away, the less likely it is to see what we're seeing or anything more extreme, which is where the p-value comes in. The p-value is the probability we saw what we just saw in our sample or anything more extreme than that. So what the p-value is telling us is how likely our sample results were given, that's the important part, given that the claim value is true. So if the p-value is small, it means that we're further away from the mean than we thought we should be. So this area would go down. Now what does that mean? If this is really small, if it's below whatever your alpha value is, so you would set alpha ahead of time. Alpha is the minimum probability you're going to leave to chance. So Z alpha or T alpha in this case, the critical number, is how far away from the mean or from the claim we're going to say could just happen by chance. So again, we're expecting things to be around in here. We're expecting the value of our test statistic when we do the sample value we get. We expect it to be in and around the claim value. If it starts to deviate away from that, it could just be a bad sample, just luck in our sample. But we have this threshold that we call the critical number, that if that sample statistic, that number that we get, goes beyond this threshold, then it's no longer just a coincidence, no longer just, oh shucks, we got a bad sample. Now there's something wrong with this claim. We're so far away from where we're claiming that we should be that I don't believe that this claim is right. I don't believe that the null hypothesis is correct. And what the alternate hypothesis is, if you remember, like in a right-tailed test, like we've got illustrated here, is that the mean, instead of it being here, or the proportion, instead of it being where we've got it located, the proportion is actually probably higher than that. And watch what happens. If I make it higher, meaning I'm moving it to the right, I'm moving the claim value to the right, then that area goes up, which is the p-value. If the p-value goes up, now that same number where we were before, that t-value, is more likely because the t-value is the area to the right or left, if you're left tail, of the test statistic. So the p-value went up when we reached our alternate hypothesis. So there's where we were. If we reject the null hypothesis that this actually is where we're supposed to be, then the alternate hypothesis is where it should be somewhere else. It should be centered somewhere else, to where what we're seeing is now more likely than what it was beforehand. So that's what the T or Z, the test statistic and the p-value are telling us. They're telling us the conclusions of our test. If the test statistic is relatively small, it's close to the value of 0, the altered mean or proportion, the standardized mean or proportion, then this is possibly not wrong at all. It could be right if this number is really close, to 0, above or below. But when it gets far away from 0, that means that that area to the right of that number is small, and this is no longer just a bad sample. It happens. We get samples with large numbers and small numbers. This is now starting to be so far away that the only conclusion that's feasible is that this number is not in the right place.